We are still talking about binary search trees. So just to remind you, a binary search tree is a tree in which the elements in the left subtree of every element are smaller than that element, and the elements in the right subtree are larger than that element. And we talked about insertions and removals in binary search trees. And we said that we have this really bad case where the height of our binary search tree increases and becomes n-1. And we've seen all sorts of operations, searching, finding the next item, removing, inserting, everything takes time OH, where H is the height of the tree. So for us, it's really important to keep the height of the tree low. And then in the last session, we saw the definition of AVL trees, but we didn't really see how you can keep a binary search tree in AVL form. So the definition of an AVL tree was that I assign a height to every node, and the height of a node is basically the length of the longest path from this node going down to one of the leaves in its subtree, right? And then just for consistency, I said that for the null nodes, I assign a height of -1 because the leaves have a height of 0. So we just assume that null has a height of -1. And then our AVL property was that if I look at any of the nodes in my tree, the height of the left subtree and the height of the right subtree should be different by at most 1. Okay. So for example, this was an AVL tree because here, if I look at this node, the height of the left subtree is 0, the height of the right subtree is 1, the difference is at most 1, and this holds for every node. Okay. Now, the last thing we did in the previous session was to prove that every AVL tree has a height that is logarithmic. So we showed that basically, if I have an AVL tree with height h, it has at least as many nodes as the h's Fibonacci number. And that's why we said that if I have an AVL tree with n nodes, it has a height of O log n. And specifically, we showed that the height is at most 2 log n, and also we showed that actually you can reduce that to 1.5. So today we're going to talk about how to keep a tree AVL. So I'm going to start with an empty binary search tree. I'm going to insert stuff into this binary search tree. And then at some point, I will violate the AVL properties. So the question is, how can I restore the AVL properties? And actually, let's do it just based on one of these two bad cases that we had here. So for example, let's do this one. I'm just inserting the numbers from 1 to n, and I'm doing it in this order. So I'm inserting 1, then 2, then 3, and so on. Okay, so let's just create a binary search tree and let's insert these items into it. So first, I'm going to insert 1. That's pretty easy. I just have it at my root. Now I want to insert 2. It becomes the right child of 1. Okay. At this point, my tree is still AVL, right? Because if you look at the heights, this one has height 0, this one has height 1, and this left child that doesn't exist, I'm assuming that it has a height of -1. And so the difference between the left height and the right height is exactly 1. Actually, the word that I use here, and I mean, everyone uses these words nowadays, is that I would say this node 1 is right heavy because the right subtree has a higher height than the left subtree. And I would show it by just having an arrow to the right here, meaning that I know that the right subtree is heavier than the left subtree. Okay, so what the AVL property says is that every node would either be right heavy, which means the height of the right subtree is 1 more than the height of the left subtree, or it would be left heavy, so the left subtree is deeper, or maybe both subtrees have the same height. So we say balanced if they both have the same height. Okay, so this is my tree right now, and it's AVL, I'm happy. But let's say I insert the next number, I insert 3, and it has to be inserted here, right? So I have 1, 2, and 3. 3 should be the right child of 2. And now I have to update all of the heights. So this one has a height of 0. Now this one has a height of 1 because it has a child with a height of 0. And then this one has a height of 2. Right. Now this is a problem because here, here my left child has a height of -1 and my right child has a height of 1. So the difference in the heights is more than 1. It's no longer AVL. And I mean, just looking at this tree, it's like a path of length tree, right? It doesn't really look balanced. So ideally, I want to turn this into another tree that is balanced, right? So if you want to create a balanced tree on these 3 numbers, how would you do it? Which number would you put as your root? 2. Yes, of course. So this is what I have. This is what I wish. I would like to have 2 as the root, and I would like to have 1 as its left child and 3 as its right child. And if I get that, then my heights are 0, 0, and 1. And it's completely balanced. I don't even have like a right heavy or left heavy note here. Everything is balanced. Okay. So I need some sort of operation that would take me from this kind of tree to this kind of tree. Okay. And that operation, I'm going to call it a rotation. Now, this is a very special kind of tree where I only have these 3 nodes. I don't have anything else, right? But in general, that wouldn't be the case. So in general, what is the case that I want to solve? So this is my general case, let's say. And actually, I'm going to call it general case 1 because there's going to be another case. So basically, the situation is that I have some node that is very unbalanced. I have a node that is, well, some people say this is doubly right heavy. Okay, so let's give that node a name. Let's just call it A. So let's say I have a node A here, and it has a right child, B. And I don't care about the rest of this, so I can have some sort of subtree here. Again, remember that I use triangles to show subtrees, and I use circles to show one single node. Okay, so I don't know what kind of subtree I have here. I just have some subtree. In this case, in this simple case, I don't have anything, right? And then I will have a subtree here, and I will have another subtree here. Okay, let's give these subtrees some names. Let's say I call this one X, I call this one Y, and I call this one Z. Now, what do I know about my heights? Let's say that the height at the root was some number. Let's call it, I don't know, T, right? So the problem I have is that at this root node, my right-hand side is much heavier than the left-hand side. So I have a situation like this where the right side is deeper. It has higher height. So what would the height of B be? What should I put for the height of B? Actually, I just remembered I write heights with green. So this is T. What is the height of B? T minus 1, definitely. What is the height of X? So here's the thing. I'm assuming that I started with an AVL tree. I started actually with the empty tree, right? And I'm assuming that this is the first time that the AVL property is violated by inserting something. So when I've inserted this new thing, it can violate the AVL property by exactly 1 unit. So this one should have a height of T minus 3, right? Because if it has a height of T minus 2, it doesn't violate AVL. I'm happy and I can just continue. If it has a height less than t minus 3, it violated AVL even before I inserted a new node. So that's impossible. So I know that this one has height t minus 1, this one has height t minus 3. Now, if I look at y and z, what are their heights? I know that one of them should have height t minus 2 by definition of height. And the other one, maybe it's t minus 2, maybe it's t minus 3, I don't know. But I also don't know which one of y and z has the bigger height. So all I know is one of y and z has height exactly t minus 2. And I also know that the other one has height t minus 2 or t minus 3. Okay, so let me just assume that z has height t minus 2 and y has height t minus 2 or t minus 3. You can also do the mirror image where y is known to have height t minus 2. Okay. Now, here's the thing. Consider this graph, consider this tree, and let's say that I run my sort algorithm on it. And remember, my sort algorithm would just print all of the items in this tree in sorted order. And that was basically using an in-order traversal of the tree. So I always print the left, then I print the current node, then I print the right. So if I print this in sorted order, what would I get? I would get X, A, Y, B, Z, right? So, and by X, I mean everything that is there in the X in sorted order. So generally speaking, this means that everything that is in X is smaller than A, and A is smaller than everything that is in Y, which is in turn smaller than B, which is in turn smaller than everything in Z. Okay? So here's the thing. As long as I satisfy this sort order, I can change the structure of my tree. As long as I create a different tree that has the same sort order. Okay, so here's the intuition on what I'm going to do. I'm going to take A in one of my hands and B in the other one, and I'm going to rotate like this. Okay, so another way of looking at it is that I take A and B, I move B up, I move A down. Okay, so here's what I would get. I want to put B as my root, and I want to put A as its left child. Because of course, if A wants to become a child of B, since A was smaller than B, it has to be the left child, right? But now I have to figure out where to put X, Y, and Z. But that's pretty easy. I know that X is smaller than Y, which is smaller than Z. So I have to put X here, put Y here, and finally put Z here. Right? And okay. Now, first of all, why is this a valid binary search tree? Because its sort order is the same as before. It's just X, A, Y, B, Z. Right? So if I just print everything in sorted order here, everything in X is smaller than A, which is smaller than everything in Y, and then everything here, all of these are smaller than B, which is itself smaller than everything in Z. And this is giving me exactly the same sort order as in the previous tree, right? So by doing this change, I didn't violate any of the binary search tree properties. Basically, the left child and the left subtree of every node only contains elements that are smaller than that node, and the right subtree only contains elements that are bigger than that node. So it's a valid binary search tree. But now let's reason about the heights. What's happening with my heights? So here's the thing. I didn't change the subtrees X, Y, and Z. So their height remains the same as before, right? So the height of X was T minus 3. The height of Y was either t minus 2 or t minus 3. I don't know which one. And the height of z was t minus 2. Okay. Actually, it's better if I do the other side because this is getting into the case that I want to show you next. So let's do this. Let's say this one has height t minus 2, and this one has height t minus 2 or t minus 3. Yeah, sorry. Okay, so I didn't change any of the heights, if you believe me. So y has height t minus 2, x has height t minus 3, z has height t minus 2 or t minus 3. Okay, what's the height of A? T minus 1. What's the height of B? E. Yes. But is this an AVL tree? Some people are saying yes. Some people are saying maybe, maybe no. So what's the bad case that can happen here? Yeah, so basically if I have t minus 1 here, but I have t minus 3 here, it's no longer AVL, okay? So if I start with this kind of tree and I change it like this, okay, let me write it like this. So if this one had height t minus 3 and I change it like this, it doesn't work. This is not AVL, okay? So what are the cases when it will actually work? Well, if I have height t minus 2, right? So in this case, if I just have height t minus 2 in both of these places, then I will also have height t minus 2 here, and it will work, right? So here's the problem that I have. I have this kind of rotation ideal, and it makes sure that my binary search tree remains a binary search tree. But it solves the problem with heights in only some cases, not in all the cases. So let's see exactly which cases are solved and which cases are not solved. So here's the thing. I was saying that A is doubly right heavy, which means that this one had a height which was 2 more than this one. So the height of B was t minus 1 and the height of X was t minus 3. Now, since A is the first node that has a problem with AVL, I know that B didn't have an AVL problem. So I have 3 cases about B. Either both of its children have the same height, or it's left heavy, or it's right heavy. Which one of these cases are solved here? So if B is balanced, if both of its children have the same height, t minus 2, you see that this works, right? So the case where it works is that A is doubly right heavy and B is balanced. This case works, okay? So let's say A is doubly right heavy, but B is also right heavy. Okay. In this case, I will have height t minus 2 for Z, but for Y, I will have a height of t minus 3. Right? So when I'm doing this, I will have height t minus 2 here. For Y, I will have height t minus 3. For A, now my height becomes t minus 2. And oh, see the magic, everything worked. Right? And actually everything became balanced, which is great. And well, the height of B even becomes t minus 1. Right? So the overall height of my tree is decreasing. Everything is getting balanced and my height is also getting smaller. This is again something that I'm very happy about. So if my A is doubly right heavy and my B is also right heavy, this also solves the problem. Okay. This is the case that we had here in this simple example. My A was doubly right heavy, my B was right heavy, And as you see, it solved the problem. It gave me a perfectly balanced tree, and it also reduced the overall height by 1. Okay. The bad case is the case where B is left heavy, right? So if A is doubly right heavy, but B is left heavy, right? Basically, this means that I have a height of T minus 2 here, and I have a height of T minus 3 here, right? Then here for Y, I will have a height of T minus 2. And for Z, I will have a height of T minus 3. So A becomes T minus 1, and B becomes T. And this is bad, because T minus 1 and T minus 3 have a difference of 2. So this is the only case where I failed. The only case that I failed was that A was doubly right heavy, but its child B, its right child B, was left heavy. Okay. So let me get back to the previous case. Hopefully I remember what I'm doing here. Okay. So we saw that this kind of rotation solves these two cases, but I have one remaining case, and I have to think about that remaining case now. But before going to that remaining case, I want to, first of all, give this a name. So what should I call this operation? Now, I always forget whether it's called a left rotation or a right rotation. And I think everyone in algorithms has the same problem. So there is this, I guess this is a right rotation because you're taking the right child and you're making it into the root. But whatever, let's call it rotation number 1. Right? So I'm just going to call this rotation number 1 on A. So if I do rotation number 1 on A, I'm just taking the right child of A and making that into the new root. Now, of course, this is not necessarily a root. Maybe this A has something going on in its parent. Maybe it's not the root of the tree. Remember, it's the first place where my AVL property was violated. So maybe it's not the root. But that's fine. If there is a parent, we just put that as the parent of B. Right? Because I'm not changing anything in the rest of the tree, so all the orders in the rest of the tree is going to work as before. Great. So this was, again, what I have, what I wish, and this was my first rotation. Now let's do another what I have, what I wish. And actually, let's try to create that bad case. Okay, so what was the bad case? The bad case was that I have some element that is doubly right heavy, but its right child is left heavy. So I have something like this. I have like a zigzag path. Let's say. What numbers can I put here? Let's say I put a 5 here. This should be larger. So let's say I put 7. And this should be larger than 5, but smaller than 7. So let's say I put 6 here. Okay. Again, I forgot the colors that I was using. Okay. So let's switch back to blue. 5, 7, 6. Now, what are my heights? This one has a height of 0, of course. This one has a height of 1. And this one has a height of 2. Now, my problem is that, as before, this one is doubly right heavy because remember, when something doesn't exist, it has a height of -1, right? But then this node 7, it's actually left heavy because, again, when something doesn't exist, it has a height of -1. Okay, so this is the case where the previous rotation didn't work. What did the previous rotation do? It took 7 and made it into the root. So let me just apply that previous rotation here. Let's say I do R1 on 5. What do I get? I'm getting this B, which was the right child, which is 7 in this case, as my root. So I will have 7 as my root. I will have 5 as its left child. And I will have 6 as the right child of 5. Now you see the problem. It's like I'm doing this rotation and kind of it's taking a zigzag path and turning it into zag-zig, I guess. So it's just mirroring my problem, but it keeps the problem, right? And I have exactly the same heights as before. Now 6 has a height of 0, 5 has a height of 1, 7 has a height of 2. Okay, so this is not what I wish, so I'm going to just, or okay, let's say, let me put it back. What I don't wish. What do I actually wish for? So again, you have a very simple tree with 3 elements. Which element do you want to force to be at the top? 6. Yeah, because I mean, I always wish for the middle element to be at the top. So let's say I put 6 here. And then 5 would be the left child of 6. And 7 would be the right child of 6. And this is a perfectly balanced tree. It's definitely AVL. And also its height is 1 less than the height of the original tree. Okay. So this is what I wish to do. But here's the thing. How can I get 6 to come all the way up here? So I want, you see 6 is kind of like the grandchild of the root. But I want to take 6 and push it all the way up so that 6 becomes root. Okay. Now I can do this directly, or I can try to just do a combination of the previous case, right? So first of all, if I have this case, I also have the mirror image of it, right? So let me actually, let me take all of these and put them on a different page. I'm really happy I'm not using a blackboard here. Okay, let's go back to what we had here. So this was a case where my root was doubly right heavy. I can have a similar case where my root is doubly left heavy, just a mirror image, right? So it would be something like this. I'm just going to basically copy the same thing. I have A here, but now B is the left child of A. And I know that A is doubly left heavy. So the exact opposite of the previous case, right? And then again, let's say I add the children here. So I have X, I have Y, and let's say I have Z. And I'm going to do exactly the same thing as before. I'm just going to take B and A, rotate it like this, so that B becomes the new root. So this is the rotation that I'm going to apply, and I'm going to call this one the second rotation on A, or maybe the left rotation, I don't know. And now this brings B on top, but A has to be the right child of B because A was larger than B. And then we have X, Y, and Z, and we add them in the same order as before. So X, I have Y here, and I have Z here. I just realized that since these are sets of nodes, it would have been better to use capital letters, but it's too late now. So again, the order is the same in both cases. If you look at the sorted order, it's X, B, Y, A, Z. And here again, I have X, B, Y, A, Z. So the left to right order is preserved. So this is again a binary search tree. And actually, you can see that this operation is pretty much the opposite of the previous operation, right? So I'm doing that rotation, and if I do this one, it just undoes the previous one. Okay. Now, so you would not be surprised to know that this solves exactly the two mirror cases of the ones that the previous one solved. So basically, if A is doubly left heavy and B is balanced, it gets solved when I do this. If A is doubly left heavy, which means like the height of the left child is 2 plus the height of the right child, and B is also left heavy, it gets solved. But the remaining case, the bad case that I cannot solve, is when A is doubly left heavy and B is right heavy. Okay. And that's actually this case, right? This is like, if this is A, if 7 is A, it's doubly left heavy, but its left child is right heavy. And again, here, I could not solve the case where A was doubly right heavy and B was left heavy. This was my bad case. Okay. So now, as you see, I mean, these are just mirror images. If you understand one of them, you've definitely understood the other one as well. But here we have the same mirroring situation. I have this bad case that I couldn't solve with my first rotation. And if I just apply the first rotation on it, I get the bad case that I could not solve with my second rotation, right? But again, this is what I wish. I wish to take this grandchild 6 and put it as the root. So can I do it with some combination of these two rotations? So look, rotation 1 takes the right child and makes it root. Rotation 2 is the mirror image. It takes the left child and makes it root. Okay? So, and again, here I can have something going up under, going on up there. And so here I have this grandchild and I want to make it root, right? So I can first do the second rotation to bring this grandchild up here. And then I can do the first rotation to bring it up one more time. Okay? So let's do this. Let's just copy this thing. Okay. I'm doing my second rotation on 7. So 7 is my A, basically. This thing. So the left child of 7 is going to go up. 5 remains where it is because I'm doing the rotation only on 7 and it's sub 3. So I'm not going to move 5. 5 is where it is. But 6 and 7 are going to be swapped now. So 6 is here and 7 goes here. Okay. Now, this doesn't solve my problem yet. Because if you look at the heights here, this one has a height of 0, this one has a height of 1, this one has a height of 2. So this one is left heavy, sorry, right heavy, and this one is doubly right heavy. Okay. But good news, this looks familiar, right? This is exactly the tree that we had here. And this is the tree that I could solve using my first rotation. So if I just now apply this first rotation, it should solve this one. And that's exactly what I'm going to do. I'm going to apply my first rotation, but I'm going to apply it on 5. So the right child of 5, which is 6, is going to come up. So now I have 6 as my root. And what happens to 5? 5 becomes the left child of 6. This is just R1. Okay. And the right child of 6 in R1, look, the right child of this in R1, it was Z. It just becomes the right child after the rotations. So I get this. which is exactly what I wished for. So again, there are two ways you can look at this. You can say that I start from here and I directly go to the tree that I like to have, right? So you can define some sort of a rotation that goes directly there. Or you can just say it's two rotations. Your choice. The important point is that in any case, we solved it, right? In any case, we got to an AVL tree. So again, this one has a depth of 0, 0, and this one has a depth or height of 1. And yeah, this is not only AVL, but perfectly balanced. And of course, again, I have the opposite or the mirror image of this as well. So imagine if instead of this zigzag, I had this one, this zigzag thing. So let's say I have this situation. It's really not that different, right? So the idea is very similar. I have the heights 0, 1, and 2. Now, again, I want to take the grandchild 6 and make it into root. So I have to first do a rotation on 5. But which rotation? It's actually now the first rotation, right? Because in the first rotation, the right child comes up. So now I do the first rotation on 5. And what this gives me is that, well, 7 is just where it was. Now 6 becomes the child of 7, and 5 becomes the left child of 6. You see, it's exactly the mirror image. And again, the heights are 0, 1, and 2. And then I have to do a rotation on 7, but which one? Now I have to do R2 on 7. And if I do R2 on 7, 6 becomes the root, 7 goes here, and 5 goes here. And again, it's balanced. So 0, 0, 1. Okay. Now I can write this in the general case, and these are exactly the cases that the previous one couldn't handle. So this was general case 1. Let me now just do general case 2. So in this case, I have A, which is, let's say, doubly right heavy. And then I have B, which is left heavy. Okay. Now, so this is the case. I'm going to also give a name to B's left child because I want to use it. So let me call this one C. And then I have X here. Let's say I have Y, Z, and oh, okay, I cannot go alphabetical anymore. So W. This is my situation. Now, again, let's write the heights. Let's say this one has a height of T. So B should have a height of T minus 1. And since this is doubly right heavy, X has a height of T minus 3. Now, C has a height of T minus 2. And since B is left heavy, W has a height of T minus 3. And what do I know about Y and Z? I know that one of them has a height of T minus 3. The other one is either T minus 3 or T minus 4. And I don't know which one is which. Okay, so again, let's say this is T minus 3, this is T minus 3 or T minus 4. It might be the opposite. I don't really care. Both cases work. Okay. Now, in this case, I want C to basically be my root. So first, I'm going to try to bring C up and replace B. So I do a second rotation on B. So A and X, I'm not touching this part of the tree. So A and X remain where they are. I have A there, I have X here. But C comes up. So C comes here. Now B becomes the right child of C, right? And then I have Y, Z, and W, so I can just put them here in order. So Y, Z, and W. Let's write the heights. So X has a height of T minus 3. Y has a height of T minus 3. Z has a height of T minus 3 or T minus 4. And W has a height of T minus 3. So now B has a height of T minus 2, which is not good because already, well, no, actually that's fine. C here will have a height of T minus 1, and A will have a height of T, and this is not good, right? Because X and C are now unbalanced, basically. They don't satisfy the AVL property. But we said that we're not doing just one rotation, we're doing another rotation because I want C to become the root. So I'm going to start from there and do another rotation, which is the first rotation on A. So the first rotation on A brings C up as the root, and then A becomes the left child of C, right? Now, what happens with the rest? I have the left child of A, which was X, and it remains here. I have the left child of C, which was Y, and I'm going to connect it here. So this is just doing R1. And I have the right child of C, which was B, and I'm going to connect it here. And of course, I'm not changing the subtree of B, so B has Z and W here. And I mean, even from this figure, you can say that it's getting balanced, right? Okay, again, the heights. X had a height of T minus 3. Y had a height of T minus 3. Z had a height of T minus 3 or T minus 4. W had a height of T minus 3. By the way, you can see that if I swap the heights of Z and Y, nothing really changes here. It's very symmetric. So it doesn't matter if I say this one has height T minus 3 and I don't know the height of this one, or the opposite. Okay, so this one now has height T minus 2. This one also has height T minus 2. And finally, my root has height T minus 1. So everything is kind of perfectly balanced, at least between A, B, and C. And my total height also decreased. But I had to do 2 rotations to reach it. Now, finally, I'm too lazy to actually do the last case for you, but the mirror image of this. Okay, is that clear to everyone? So it's just that, just mirror this. I have this A that is doubly left heavy, and it has a child B that is right heavy. I'm going to do exactly the same thing, except that I'm first doing a rotation of type 1, and then I'm doing a rotation of type 2. So mirror image of the above works for the case where A is doubly left heavy and B is right heavy, right? So again, this was the case where A was doubly right heavy and B was left heavy. Great. So after all of this, I finally know how I can make my tree into an AVL tree, right? But this is just for insertion. Before moving forward, how much time does each of these rotations take? So for example, if I look at R1, how much time do I need to do R1? Yes, it's constant. Because if you look at it here, what are the pointers that I'm changing in my tree? I'm not changing any of the pointers in X, Y, or Z. All I'm doing is that I'm changing the pointers of A and B, right? So I'm changing at most 4 pointers. Right, so the left child of A, the right child of A, the left child of B, the right child of B. If you have parent pointers as well, I'm changing maybe 8 pointers at most, right? But I'm changing a constant number of pointers to do this rotation. So this rotation is constant time. This rotation is just a mirror image of the previous one. So with the exact same argument, this is also constant time. And finally, these cases were cases where I would do 2 constant time rotations, but 2 times a constant is constant. So in all cases, I'm taking O1 time. But here's the thing. How does my insertion actually work? So when I'm inserting, I have to basically insert as before, right? Which means that I start at the top of my tree and I'm basically doing a search for where this item should end up. And then I insert it. But as soon as I insert it, the heights in all of its parents, all of its ancestors might change. Maybe they don't, but maybe I'm unlucky and the heights change. So I have to start going up. And whenever I see that a height is not correct, whenever I see that the AVL properties are violated, I have to do the rotations, right? But again, the height of my tree is at most log n because it's an AVL tree now. So I'm screwing up the height for at most log n, or actually O log n ancestors. And for each of them, I'm going to do 1 or 2 rotations. So to fix everything and make sure that I have an AVL tree again, I'm doing at most O log n rotations, right? So my insertion time remains O log n because I'm just doing the previous insertion, which took O log n, and then I'm fixing all of this. So let's say insert as before. Actually, let's say if I have insert X, I just say do as before, but then fix every ancestor of X. Of course, you only fix the ones that need fixing. So fix every ancestor of X that violates the AVL property using rotations. And based on which case we're in, you're either going to use 1 rotation or 2 rotations, right? Okay, this is for insertions. What happens if I want to remove some item? Again, it's exactly the same thing. I find my item X, I want to remove it. First of all, we said that we can remove X only if it has only 1 child or 2 children, or no children, sorry. If it has 2 children, I have to first swap it with the next item. So I do that. And then basically, whenever I'm removing something, now I'm removing a leaf. Or I'm removing a node that has only 1 child. When I remove it, only the heights of its ancestors can change. So again, it's the same thing as here. I just remove it, and then I go into all of the ancestors from the bottom up. And whenever I see the AVL property is violated, I do rotations to make sure it's restored. Okay, so remove X is the same. Now, if you look at all the other operations that we had search, we had the operation rank, which told us how many elements are smaller than some particular element. And we also had like next item, previous item, minimum, maximum. Those operations do not change the tree at all. So I can keep them as they are. I don't have to change anything for them. But one important point is that we used to keep some extra information. For example, when I wanted to do rank, I had this problem that I needed to know the size of the subtree of every node. This was some augmented information that I was saving at every node of my tree. Now I have to be careful. Every time that I do a rotation, I have to update that extra information and I have to update it correctly. So if you have a tree that also is keeping track of the size of every subtree, every time that you do the rotation, you have to be careful about the sizes. But again, that's not too hard because we had this function update size, which basically updated the size of a node based on its two children. And if I have a rotation like this, I'm not changing anything in X, Y, and Z. So the only places where the size can change are basically A and B. So I just call update size on A and on B. But a very common error is that people call it on B before calling it on A. So be careful. You have to update from the bottom up. You have to update A first and then update. Yeah. So that's it. I will actually probably record a video of me coding this because I like to suffer. And I'll put it on Canvas for you, and I'll put the code there as well. But maybe try to code it in C++ yourself too. Okay, just one last sentence. Finally, we have a binary search tree whose height is guaranteed to be O log n. So all of these operations are now logarithmic time. Everything is O log n, which means that I can use this AVL for sorting. If I want to sort n numbers, I would just insert all of them into my AVL tree, and then I call the sort function. I basically print them in sorted order. And this is also optimal because this is comparison based, and we've seen before that you cannot do comparison based sorting in less than n log n time. Okay, see you tomorrow.